Well, good afternoon. This is 2:33, so we're 3 minutes late getting started in differential equations class, but I'm the only one in the room right now, so we're going to get started. I'll wait and make my announcement for 14 seconds. So I think it just lost it. And here's what the problem is. See, it was far worse than this. The bar was across here, and I don't know why it was there, but I couldn't get to my buttons down here because this was on top of it. Now I'm able to get to them, but before, so anytime I try to stop it, it would, to change to eraser or whatever, it would go back to the beginning. I don't know why, and so it was just doing some really, really weird stuff. So where we are here, this is example 9 on page 127. But before we go there, I had some announcements to make, and let me go on and make those since I have a body in the room to hear them. Otherwise, I wasn't sure anyone would even hear it, especially since it lost its mind there. They came out over the weekend. I think they sent them to students as well, or at the end of last week, the final exam schedule. And I just printed it off and was announcing it to classes until I happened to see that they have the final exam starting on Monday, April the 29th. But in the college calendar, the academic calendar, Monday the 29th is the last day of class. And the finals start on Tuesday, April 30th. Okay? And so they have the last ones being Saturday, May 4th. But on the academic calendar, it says finals end on Monday, May 6th. So they've got it screwed up, okay? I've got to see what I can do. And then the rest of it makes is sort of messed up too. They say that all grades are due in by noon Monday on May 8th, which can't be the case because that's when finals are happening. And they say graduate grades are due Friday, May 4th. What I think they did, they just changed the 18s to 19s. Well, I don't know what they did. It's really screwed up, so I don't know when finals are. But of course, in this class, it's going to be a take-home final. Are you graduating this term? Okay, so you don't have to worry about that. Get it into at the end of the term. And this I know you're interested in. Are you the next Miss Lawson State? So if you're interested in this, there is an entrance forum on the Birmingham West Campus, just barely, in that new Academic Success building, right on Wilson Road there. But you can't get to it from Wilson Road. You have to turn in and pull in behind it, which they call the front of it, even though it's facing away from the road. So I don't know. But that's from 2 to 4 today, which is probably already happening now, isn't it? Yes, we're past 2 o'clock. Yeah, we're past 3 o'clock. Okay. So it's happening now. But you still have tomorrow, because tomorrow it's going to be on this campus from 11:30 to 1. We only take an hour and a half. They took 2 hours over there. I don't know why. Maybe they got more people. I don't know. But anyway, that's in this building, Building A, but room 182, which is the testing room down there right on the other side of the main desk. Go back that little short hallway, and to the left there, you'll see the testing room. And that's 11:30 to 1 tomorrow, if you know of anyone who's interested in being the next Miss Lawson. Requirements are currently enrolled at Lawson State Community College, 3.0 cumulative grade point average, completed or currently enrolled in a minimum of 16 credit hours at the 100 level or higher, and active in an extracurricular activity organization. And for more information, Ms. Leslie Harper and Ms. Deneen Jones are both on the Birmingham West Campus. I think they're both located in that new Academic Success building, and Ms. Kimberly Moore is here in this building, right there at the testing room. Dr. Herndon's office and her office are right there at the testing room. Okay. And then, I don't know, are you at all thinking of going to Alabama State for your next? No. for anyone who may be, today, this morning, there was an official signing of a memorandum of understanding between President Ward of Lawson and President Ross of Alabama State, signed some special agreement, and that obviously I think must make it easier for students to matriculate straight from here to there with maybe fewer hassles. Okay. So anyway, that happened this morning as well. Now, and you do, I think I mentioned last week, we have no class on Wednesday because I have to be in Montgomery. Yeah. So I will not be here Wednesday for this class or any of my classes. I might get back in time for my evening class, but they said they didn't want to come and then sit and wait for me. So we're all going to do the same thing. At the end of class today, I'll show you on YouTube where to go to get Wednesday's class, and then we'll pick up the following Monday after that. So they don't fit exactly, but they'll be the closest I can get to what we've been doing here. Okay. You don't have any classes on Thursday. No. Thursday is the Honors and Awards Day here, so that's another day that's messed up because of this. Losing a day on Wednesday, if they take away a Monday, that's 2 classes we've lost. It's such a pain in the neck. Okay, but anyway, we're on example 9, top of page 127. We got 3 functions here, e to the x, e to the 2x, e to the 3x, and the claim is all 3 of them satisfy this third-order differential equation, and I took the 3 derivatives of all 3 of those, and we plugged them in here, and sure, it's all true enough, they all added to 0. Now we're seeing if they're linearly independent of each other, and there we use the Wronskian. Now, the Wronskian in 2 dimension was pretty easy. In 3 dimensions, a little more involved, but what you do with the Wronskian, you do a determinant. Okay, and this is where it all came from. I was trying to get to erase because I thought I need more room here, and I finally got it erased, but then it wouldn't come back. I mean, I couldn't get the recording to come back. So here's what you do. You put the 3 functions on the top row, e to the x, e to the 2x, and e to the 3x here. And then for a 3 by 3, you do this. Repeat the first 2, e to the x and e to the 2x. Okay? Then you put the derivatives, first derivatives on the next row. That's e to the x, 2 e to the 2x. Remember how to do derivative chain rule? Right, okay. And here, this is still there. And then we'll have a 3 e to the 3x, and then repeat the first 2, e to the x and 2 e to the 2x. And then the second derivatives here, which again would be e to the x, 4 e to the 2x, 9 e to the 3x, e to the x, we'll be repeating that one, and 4 e to the 2x. Okay? Now I'm going to put the determinant bars there, though you can't do a determinant on a 3 by 5. It only is a 3 by 3, but this is just so we can do the determinant the easy way. And that's going to down the diagonals here, and that would be a 18 e to the 6x. This one going down the diagonal would be 3 plus 3 e to the 6x. And this last diagonal here will be a plus 4 e to the 6x. And then you go the up diagonals, but these are negated, so this will be a minus 2 e to the 6x. This one would be a minus 12 e to the 6x, and this would be a minus 9 e to the 6x. Okay? I'm sorry?
That second one that you did, the one coming down. Yeah. Oh, okay. We got
that is part of this one. Sorry.
We got a 2x. Okay. I didn't see
right there.
I didn't see the 2x. Yeah. Up there. All right.
Okay. Yeah. And since they're all e to the 6x's, we can just factor that out, and we hope that our coefficients don't add to 0. If they do, that means they are not linearly independent. If they add to anything other than 0, they are linearly independent. So let's see, we have 3 positives, and that's 7 and 18 or 25, and the 3 negatives would be minus 11, and minus 12 would be minus 23. So that gives us 2e to the 6x, which is not equal to 0, so therefore they're linearly independent. Okay? So, 2e to the 6x. All right. Now, and they are true for all real values of x, so the functions y1, y2, and y3 form a fundamental set of solutions, so therefore our general solution would be to take these 3, and the general solution y would be c1 e to the x, that's the first of these, plus c2 e to the 2x, plus c3 e to the 3x. That would be your general solution for the third order differential equation. Just take the fundamental set, which because they're all solutions and not linearly independent, that they are linearly independent of each other, then you plug and just assign a coefficient to each one. For some reason, my plus did not show up here. There, the top part of it did, but that's all. Okay, so that's it. And it could have been a minus there too. It doesn't matter, but usually the pluses. So that's your general solution. Since it's a third order differential equation, you only need 3 independent solutions. Anything more than that is not going to be independent, or it's not going to work. Okay. So it shows you the 2 things you got to do: verify that they are solutions, and then verify that they're linearly independent. And that's what the Wronskian does for us. If those 2 are done, then write them down. Okay. You only need the number of independent coefficients here that you have a degree of the differential equation. Okay. Now, let's see if this does anything. I bet you it won't do it completely. Yeah. Notice here, we can't get rid of that because that's the one that ended. So what I have to do here is get away from that and how do I do this? Okay, don't save. Okay, and then open this back again. Clean. It better be clean. But it takes a while for PowerPoint to open again, and it's just 3 slides. Okay. And we'll go from current slide and go back to where we were. All right. 4.1.3, non-homogeneous or non-homogeneous, or however you want to say that, equations. Any function y sub p. Oh, I've got to go back and get my colors back. Okay, such a pain. Y sub p, that stands for particular. Any function y sub p free of arbitrary parameters, c1, c2, or anything like that, that satisfies and if you go back to equation 7 on page, it's several pages back, 121, I believe it is. You see under 4.1.2, homogeneous or homogeneous equations, the second one there, number 7, is one with a g of x at the end. Okay. So any y of p, free of arbitrary parameters, that satisfies that number 7, okay, is said to be a particular solution. That's what the P stands for, particular solution. The other are general solutions, or characteristic solutions. We'll call them by several different names, but those are that. This is particular solution. If you had a constant function, y sub p of equal to 3, okay, that is a particular solution for the non-homogeneous equation y double prime plus 9y is equal to 27. Okay? Because, take the first derivative of yp, and what do you get? 0. Second derivative? 0. Okay? So second derivative would be 0 plus 9 times 3, 27. That's equal to 27. So obviously, that is a particular solution. And you don't need to put a coefficient in it or anything else. That's just a solution. No C1, C2, or anything else. That's just a solution. The y double prime and 9y, you can go through and do it. You'll find out later that's cosine of 3x plus sine of 3x. Okay? Those will be the y's that will work for that for your characteristic solution. But for the particular solution, this one will work. Because, see, this is non-homogeneous. If that had been equal to 0, then yp would be 0, and that would be anything. You know, so we don't need that. But that will work here. Okay? Now, so let's imagine we've got a bunch of these. y1, y2, y3, ... up to y sub k. They've gone to y sub k now. Okay? Let's say these are solutions to the homogeneous case, where this is equal to 0, not 27, or not anything else. Okay? They're solutions to the homogeneous case, and y sub p is a solution to the non-homogeneous equation. These are to homogeneous or homogeneous. These are to, this one to the non-homogeneous or homogeneous, or however you want to say it, blah, blah, blah. Okay. Okay? If that's the case, then your general solution will be this. C1, y1, plus C2, y2, plus C3, y3, plus ... all the way up to and including C sub k, y sub k. Those are your ones for the homogeneous case, and then you'll throw n at the end plus y sub p, the one that is a solution to the non-homogeneous case. That's now your general solution for a non-homogeneous linear differential equation. Okay? All right, so the theorem that follows that, which is pretty much just repeating what we were just saying. What's that? Oh, yeah, is this one. Let me erase this. Now that I look at this, we may have been 14 minutes in, which wouldn't have been too bad. So maybe we didn't lose any. I thought that was 14 seconds, but it was 14 minutes. So maybe I didn't lose any. I don't know. We'll see. All right. Let y sub p be a particular solution for the non-homogeneous or homogeneous linear nth order differential equation. Okay. Solution, I abbreviate like crazy. Of the non-homogeneous and differential equation. I should say, yuck. My eraser's not picking up. There we go. All right. This is where it messed up before. I hope it's not getting ready to again. Be any particular solution of the non-homogeneous or homogeneous linear I forgot to put that in. That's important. Nth order differential equation. We're not saying ordinary anymore because they're all ordinary. Okay, differential equation on an interval I. Okay. And let these, your y sub 1, y sub 2, y sub 3, dot, 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 up to, they go back to k or n. Now they're back to n, y sub n, be a fundamental set. That's what they call it. The fundamental set of solutions, okay, of the associated not are homogeneous or homogeneous, okay, differential equation. Goodness gracious. Okay, on the same interval I. Okay, then the general solution on that interval general solution is y is equal to c1 y1 plus c2 y2 plus c3 y3 plus dot 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 plus c sub n y sub n plus y sub p. Okay, that will be your general solution, where your ci's for I less than or equal to 1 less than or equal to n, okay, are your, well, they say I equal 1, 2, 3, 4 up to n, okay, so the arbitrary constant. Okay. They do a little proof here, and they go back to the linear operator if you want to go back and trace down and remember what that is. Basically, if you haven't gotten it by now, okay, let me say one thing. Remember they said particular, okay, YP is a particular solution. Y1, 2, 3 are the fundamental set of the solutions. Now remember what's included in that fundamental. That means they're all solutions. And by the way, it's an nth order differential equation. So you have n of these, but to be a fundamental set, they have to be linearly independent. If they're not a fundamental set. So if you have n fundamental solutions in that fundamental set, you've got them all. You've got all that you need. Now, you might have another one that could substitute for one of those and still be fundamental, but you can't add it to the set because as soon as you do that, you're now not linearly independent. Again, so that's what it means to be fundamental set of solutions. They all have to be solutions and they have to be linearly independent. And if you got that, then that's all you need. You don't need any more. But if you got, that's for the homogeneous or homogeneous. But if you have a non-homogeneous, then you need at least one particular solution to handle the right-hand side, which is not 0 now. Okay? Now, I think we'll see later. Well, we'll wait and see what we see later. Okay. Now, as if we didn't have enough names for them. Okay? We see that in that theorem, 4.1.6, one that's right here, that the general solution of the non-homogeneous or a non-homogeneous linear system consists of the sum of two functions. These functions here we call the complementary solution is called the complementary function. And this is the particular. Okay. Its pen is acting strangely again. Okay? So, the general solution is your complementary solution, y sub c. Y sub c, not c sub y. And your general solution is the sum of the complementary plus y sub p, which is the particular. Okay. Now, and it says any particular solution. So you don't need to list them all, just any particular solution that would solve that right-hand side, which is not 0. Okay. So let's try example 10. Okay, how are we doing on time? We got, yeah, we got, what, close to 20 you said?
15.
15, okay. Now, by substitution, the function y sub p is equal to minus 11/12. What a beautiful number that is. One of my favorites of all time. Minus 1/2 x. What a wonderful particular solution. Is readily shown to be a particular solution for the homogeneous or homogeneous differential equation y triple prime minus 6y double prime plus 11y prime minus 6y equal 3x. Well, 10 o'clock scholar. Okay. You know, I forgot to mark even you here because I hadn't turned the page yet. Well, nobody was here at first. So today is the 8th. All right. Daniel's here. And Muhammad is here. Okay. You know, but you wouldn't be here anyway, there is no class Wednesday for this class, okay, because I have to be in Montgomery. And at the end of the class today, I'll tell you what to look at on the YouTube videos to cover Wednesday's class. I think that's how we decided to do it, right, rather than make up a class. Okay. So, now, I can't remember if you were here for it or not. Well, you were, but you caught this the tail end of it. This is, when that's equal to 0, that was a homogeneous case for the ones we just did. E to the x, e to the 2x, and e to the 3x. The one we were working on when you came in. Okay? That is, with that equals 0, so that would be your characteristic solution. I mean complementary solution. That's all these names. Okay. To write the general solution, we must also be able to solve the associated homogeneous solution. But guess what? We just did. Our complementary solution, y sub c, is what we were calling the general solution of the homogeneous case. That's now the complementary solution of the non-homogeneous case. That's c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. That was the general solution for the homogeneous case where that 3x was a 0. It's now called the complementary solution for this same differential equation when it's a non-homogeneous. Okay. Now, so they say here, they say by substitution it is readily shown to be a solution to that. Well, let's see if it's readily shown. Yp prime would be what? There's your Yp right here. If my pen would write, there would be my Yp. There. This is such a pain in the neck. Now it writes 15 times. No. y prime would be negative 1/2. Right, there's an x. Right? Okay, y double prime, yp double prime, that would be 0. And yp triple prime, that would also be 0. Okay, so if we plug that in, what we would have would be 0 minus 6 times 0 plus 11 times negative 1/2, that's your y prime, minus 6y, is that equal to 3x? Okay, well, what is your x? Y, that's this particular solution. That would be, so I should have plugged that in. Let me go back and do that. Okay. All right. 6 times, minus 6 times y, which is minus 11/12 minus 1/2 x. Goodness gracious, this pen is so crazy. Okay. The question is that equal to 3x? Well, let's see. This will be minus 11/2 plus 11/2. I say halves and write 12, so I don't know what's wrong with my brain here. And sure enough, that is. Wait a minute. Oh, yeah, okay. Plus 6 times minus 6 times minus 1/2 x would be plus 3x. And that, sure enough, is equal to 3x.
How did you get the positive 11/2?
Up there?
No,
Oh, here.
Yeah, right.
Here. Okay. Minus 6 times minus 11/12. 6 will go into 12 twice. Minus times minus is plus, so you get 11 over 2. Okay. That was a minus 11 over 2 plus 11 over 2, and then this is plus 3x. And that's equal to 3x. So, sure enough, that would work. And you only need one. There may be others that would work, but that's one, so that would be it. So the general solution for this differential equation, this non-homogeneous or homogeneous, would be y is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x minus 11/12 minus x over 2 minus 1/2 x. I was just running out of room, so I wrote it that way. That will work, okay? They put 1/2 x, I put 11/12. Now, remember, a superposition principle is what got us these C1s and E1s, all those, that kind of things. C1, F1, and C2, L2, and C, yeah. Superposition there. Here's another superposition principle, okay? Can I erase what's up here? You still writing? Okay. All right. Yeah, we did lose some time because this says we only have 33 minutes recorded. The first part of the class, the thing went walkers on me, and it went back and started and erased the first part of the class. And that was right before Dan came in. I was trying to fix it when he walked in, so I couldn't get it back. So you can follow it in the book, though. Okay. Okay. Do we have time for it or not? Yeah, we do. We've got plenty of time. Okay. Here's another superposition principle. Let y of p, y sub p 1. Now they have a bunch of these. Y sub p 2. It's y sub p sub 3. Okay, as if you had enough subs here. Dot 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 up to and including, this will be k, y sub p sub k be k particular solutions of a non-homogeneous linear of a non-homogeneous linear nth order differential equation on an interval I, corresponding in turn to k distinct functions G1 of x, G2 of x, G3 of x, dot, up to and including G sub k of x. So in other words, you have a non-homogeneous solution, differential equation that has all the differential part here equal to not 0, but not just a g of x, but a g1 of x, plus g2 of x, plus g3 of x. So you have all these functions out there on the right-hand side that make it non-homogeneous, but you have a bunch of them. So if you find a particular solution for each one of those and add those together, superposition, that works well, okay? And you don't need any arbitrary coefficients with them because they're particular solutions, okay? That is, suppose that y sub p of I denotes a particular solution of the corresponding differential equation. Goodness gracious. So here I'm going, the thing that they've been avoiding writing again, they're writing now. A sub n times x of x, times the nth derivative of y, I'm not going to put of x, but y is a function of x, plus a sub n minus 1 of x times the n minus first derivative of y with respect to x, plus a sub n minus 2 of x times y to the n minus second derivative of x, okay, plus plus a sub 2 of x y double prime plus a sub 1 of x times y prime plus a sub 0 of x, I can't write, that's a sub 0 of x times y is equal to g sub I of x, okay. So your y sub p of I corresponds to each one of those. So you have I different things. That would be G1 of x plus G2 of x plus G3 of x, any of those, and you have a particular solution for each one that is a different one there. Okay? Then y sub p, another sort of general one, of, I think they put of x, yeah, is equal to the y sub p1 of x plus y sub p2 of x plus y sub p sub 3 of x plus plus y sub k, wasn't it? I keep losing track of what, yeah, y sub p sub k of x. Okay. All right. Then again, a superposition here, the difference being no arbitrary coefficients. For the complementary solution, for the homogeneous part, you need arbitrary coefficients for every degree of your differential equation. Okay? This one, the n's and the k's have nothing to do with each other. If you have a sum of a bunch of these, 3 of them, 15 of them, or whatever, but this was just the fourth derivative, yeah, doesn't matter, you know. Then you have a y sub p for every one of your g sub i's, okay? I going from 1 to k, okay? Blah, 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 blah. That's a particular solution for this thing here, where your g is now g1 of x plus g2 of x plus g sub 3 of x plus dot 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 plus g sub k of x. Okay. So if you had a whole string of them there, you have a particular solution for each one. All right. Do we have time for example 11?
We got 5 minutes.
5 minutes. Let's see if we can. I don't think it'll be so awfully bad. Okay. I think now that I think about it, what happened when I was trying to get to this, I believe it must have hit something up there and stopped the whole thing. So, sorry about that. Let's do example 11. Okay, no, I don't think so, because we first have to verify. So, not quite. I don't think we'll have time to verify and show it. So we'll stop right there at 11. We almost finished 4.1. I mean, we have one example left in 4.1. So homework exercises here would include, many of these you've heard before, any of either 1 or 3 if they're in the back, 5, 7 if they're in the back, 9 if it's in the back, 11 if it's in the back, 13 if it's in the back, that's in 4.1.1, 4.1.2, 15, any of the odds 15 to 21 if they're in the back, any of the odds 23 to 29 if they're in the back. The non-homogeneous equations, those are the ones we're just working on, any of the odds 31 to 35 if they're in the back. Okay. Most of the discussion problems are not in the back, so I usually don't assign those. Okay, so we're going to pick up then next time there. We'll do that last example in 4.1, and then we'll go to 4.2. So what I'm going to do now is get out of this and show you where to go in YouTube. Okay? So I'm going to show you in Blackboard because that's how you would do it. Now your Blackboard may look not just like mine because I'm in the instructor mode, you're in the student mode, but hopefully it'll be close enough you can see it. I'm recording this still so other people can see it too. I have to log in just like you do, but if I spell my name right, I do. Okay. Not sure I got that spelled right either, but we'll see. Yeah, it must have worked. Okay, then I go to the course. Ah, there it shows up here. I have a lot more courses than you will have. They go back a long time. Okay, there's this term's course, of course. And you go to handouts, PowerPoints, and more. Hopefully that's where you've been going. Okay, remember this is where the syllabus is. That's where my locator card is, and this is where everything else is. So if you go to handouts, PowerPoints, and more, there's your research paper instruction, and there's two different places that have some videos available. You may or may not find helpful, but here are ours. Math 238 YouTube videos. That's ours. You click on that, and then at the very top up here, what we're looking for is something around 4.2. These are some left over from a long time ago, so let's just scroll through those until we get down here. Here we go. Okay. The 4.2 to 3, no, 4.1 to 2, that's the one you'll start with. So do these two here. 4.1 to 2, because that obviously finished that, and start at 4.2, and 2 to 3 was where we will. So I'll start next time with 4.3 to 4. I'll find out where that one starts, and that's where we'll start next Monday. So you go over these. There's just going to be a little bit in this one that is also, you know, starting with that last example, what was it? 11? Yeah, example 11. That's where you'll start. Anything earlier in 4.1 you don't have to do unless you just want to. And then it starts in 2, and this continues in 2 and gets up to 3, and then we'll start wherever that begins in 3. So we'll start replacing video 11. So you do those 2 at home. There won't be much of this one, just a little bit, and then there'll be that one. Okay? Make sense? All right. Then I will close this out, close that out, and we'll end the thing. Oh, a minute early. I'm cheating you out of your tuition dollars today.
Man, how wasteful.
I know it.